everyone, welcome. My name is Brittany Todd. I'm a member of the Fabric Leadership Team. Thank you all for joining us today and for the second installment of our Stitching Together Innovation with Fabric Users featuring Joaquin Chung. Next slide, please. Before we begin, I would like to share a few housekeeping items. The webinar will include a live question and answer session following the presentation. Please note that the chat feature has been disabled. If at any point you have a question, please type it in the Q&A box at the bottom of your screen, and we'll answer it during the Q&A session. Last, this webinar is being recorded and will be shared with all registrants. Next slide, please. We are joined today by our presenter, Joaquin Chung. Joaquin Chung is a research scientist at the Data Science and Learning Division of Argonne National Laboratory. His work spans diverse areas that go from designing systems for enabling memory-to-memory data streaming between federated instruments to architecting of future quantum communication networks, to exploring advanced wireless networking for scientific use cases. I will now pass to Joaquin Chung to start the presentation.
Thanks, Brittany, for the kind introduction, and thanks everyone for joining and for your attention. So this is the agenda for today. I'm going to introduce SciStream, which is a tool for enabling federated data streaming. So I will motivate this with some use cases, some explanation about federated scientific streaming, and then I will show the SciStream architecture. From that, we will move on of why we decided to use Fabric for our experiments, and I will show some examples of publications that we have already done about SciStream, and we will conclude with a student showcase that demo how to deploy SciStream on the Fabric testbed for your own experiments. So yeah, let's go into the introduction to SciStream. So let me motivate SciStream with the streaming processing in science use cases. And I'm going to use here the light source facility as an example. A light source is a large instrument that uses very bright light that is shot into an object to study the diffraction patterns and then observe phenomena that is happening on the object, or study the material and composition of the objects. Here you can see the Argonne Advanced Photon Source, or APS, that was like probably a month ago upgraded to being able to transfer data at hundreds of gigabits per second. So we envision that experiments that generate this amount of data have to be analyzed at a high performance computing facility. So the analysis happens in a remote site, and then if this can be near real time and we can provide low latency feedback, we can visualize and even steer the instrument to focus on more interesting phenomena that is happening with the objects. So how these instruments and these experiments work right now. So typically, you will have instruments and HPC in different security domains. And state of the practice is that this is going to happen via file-based data transfers. So you will run your experiment, write your results into a shared file system, then use a data transfer node that is deployed at a science DMC to move this data over a wide area network into the data transfer node into a parallel file system at the HPC center. Then your computing nodes will read from this parallel file system, execute the analysis, and you will obtain your data, call it post-processing. But if you want to enable streaming processing, with the current infrastructure, is not that straightforward. So you have your instruments on private networks and HPC as well. They are protected by firewalls, so they are not visible from outside. That means that scientists need to negotiate with each institution to open ports, and then so they are able to stream the data. They also need to implement mechanisms to comply with the security policies of each institution. Then there is the use case in which they are still in different security domains, but they have public IP addresses. We can argue this is probably easier, but some challenges remain. So the scientists still need to worry about the TCP ports needed to stream data. These IP addresses are not gonna be known until you get your allocation in the HPC. And even if all these are reachable over the internet, you still need to authenticate your connections for security reasons. So what is the future with SciStream? SciStream is a secure streaming, enables secure streaming between security domains. So if we go back, you will have your instruments and in their private area networks connected to a gateway node deployed at a science DMC. There you can deploy SciStream's software tools. This one we call the SciStream Control Server, or S2CS, that will deploy the SciStream data server that is a proxy that on demand will enable these bridges between the LAN and the WAN. Same thing happens at the HPC facility. So as I mentioned, SciStream will automate the process of deploying these secure bridges between security domains. It keeps the streaming application semantic intact because you now have to listen on local IP addresses from your local pool. You don't have to worry about IP addressing outside of your institution. It requires minimal changes to the application to interact with SciStream. It supports a lot of applications because we have developed SciStream to run on the transport protocol layer, and it uses globals out for federated identity and authentication. So this is S2UC is the software tool that allows users to interact with SciStream deployed on different infrastructures. So this is a more complex diagram of the architecture and the control protocol of SciStream. It can be a little bit intimidating, but I invite you to look at our publication at HPDC 22, where we propose the SciStream architecture, and we explain this protocol and other components of the architecture. So what are the technical features of SciStream so far? So in the last two releases, 1.0 and 1.1, we have integrated HA proxy, Nginx, and S-tunnel for production-grade forwarding quality on the data plane of SciStream. We have integrated with globus out for federated identity. We have data channel authentication, allowing ports to be opened securely. We implemented encryption for control and data channels. So we use a TLS protocol for the control channel and pre-shared key authentication for the data channel. And you can find the open source code in this repository and the documentation here. We will show this again at the end of the webinar. So why did we decide to go with Fabric? So to explain this, let's go back in time before 2022. So we were developing SciStream, and at the moment we wanted to evaluate the performance of SciStream data plane. So this idea of using proxies to create these bridges. At the moment, our option was Chameleon Cloud. If you're familiar with Chameleon, you can request bare metal nodes, and back then, Chameleon will allow you to deploy nodes with 10 gigabit per second Ethernet connections. We were also able to get a InfiniBand, but I'm not gonna show these results here. I'm gonna go a little bit fast over here because I want to show the demo, which is longer, and you will learn a lot about how to deploy SciStream. So the methodology for this initial experiment was to compare a streaming application running on a SciStream enabled infrastructure versus the same application when producer and consumer have direct connectivity. That ideal case in which both instrument and HPC are reachable over the internet. And for this, we measure goodput, the added latency, and intermessage delay variation. That is just another way of saying jitter, but we were not measuring jitter at the network level, but at the application level. So this is just one set of results from the experiment where we use a real wide area network. At the time, Chameleon had only 2 sites, the University of Chicago and TAC in Texas, and the RTT between the 2 sites was 30 milliseconds. So these are the results for goodput as a function of the sample size. So when I mentioned sample size is because we were using a publisher subscriber application written on Python on top of 0MQ. And we will put messages on 0MQ and then publish them to the consumer. So we evaluated three types of proxies or ways of implementing SciStream S2DS compared against no SciStream. We can see that L4 and L7 proxies were very close to each other in performance. NAT is probably we're making a disservice to NAT here in that paper because we just implemented IP tables on an unoptimized Ubuntu version. So here is the intermessage delay variation. Something interesting that we noticed is that for small sample sizes, we had more jitter, and then for larger, everything was closer, specifically for our layer 4 proxy. So that triggered us to do a little more investigation, and we figured out that our L4 proxy was so naive that it was in fact an application layer proxy because it was reading from one socket, putting data on memory or file, and then reading from there into another socket. This was creating a lot of context switching between kernel and user space on the operating system. So we decided to give it a try to eBPF. And this talk is too short to just give you an intro to eBPF. That's probably, we can have another whole webinar for that. But eBPF will allow us to push most of the logic into kernel space and reduce the context switching between user and kernel space. We will create sock maps and have buffers. So it has its pros and cons, but you can read the paper that we published in this 2022. And then here, we use Fabric for our experiment. And then this is finally I'm answering why Fabric. So as I mentioned at the very beginning of the webinar, we are expecting this streaming data analysis to be hundreds of gigabits per second. Fabric by default gives you 100 gig on the wide area network. So we were able to deploy our linear topology that has producer, our SciStream S2DS, the wide area network, our consumer S2DS, and then our consumer, all at 100 gigabits per second. And then we can also have our control network that we use to run our S2UC to request the configurations that we wanted. Given the nationwide scale of Fabric, we were able to experiment with 5 topologies with different RTTs. So we had something that was able to mimic a LAN, a metro network with all 5.5 milliseconds closely, a short one, and then a long one with 143 milliseconds RTT. Here we again measure the good put, perceived delayed, and jitter. In the interest of time, I'm only gonna show the jitter, the good put results for each of the RTT of the networks that we emulated. And this is actual network traffic. There is no TC involved here. All the RTTs are real. And this is the good put that we obtained. We, again, were comparing a no SciStream use case against our legacy proxy, which was the naive implementation, and the SOCMAC eBPF. And you can see that for smaller, shorter distances, of course, SOCMAC outperforms the legacy proxy a lot in the metro case. And there's a significant, and you can see that we're on SciStream, we're able to go really close to the line rate, 70, close to 70 gigabits per second. Then when we go to the larger sizes of the wide area network, we surprisingly see that our naive proxy was performing really close or even better than SOCMAP. As we mentioned in the paper, SOCMAP has small buffers, and this application level proxy has larger buffers. So there is a trade-off in everything, and this is the things that we were able to discover with Fabric. So right now I'm gonna switch to the student showcase, the demo prepared by Acheme. He's a first year PhD student at Clemson University, working with Professor Casey Wan. And yeah, let me bring up the recording because he's traveling today, so he wasn't able to join us. Start from the beginning.
Hello, everyone. You've been introduced to SciStream, and in this demo, we'll walk you through the process of deploying SciStream on the Fabric testbed. We'll showcase the deployment across a 4-node topology, simulating real-world conditions where producers, for example, scientific instruments, and consumers at, say, remote HPCs, are separated by a wide area network. There are a few requirements to installing and using SciStream, as we want to demonstrate here today, including having Docker. We can just use a Docker image in Fabric to meet this requirement. We need external, which SciStream will use to set up a secure proxy, Python 3, and with IPEF 3, we will show a secure memory-to-memory data transfer between a producer and consumer using SciStream. I already have my notebook open, and I opened 4 terminals on my Jupyter Hub, which we're going to use later during the configuration steps. We'll begin by importing the FabLib library, a powerful extension of the Fabric testbed, which simplifies the management of computing and network resources. This library will enable us to create and manage slices. And a slice is an isolated set of resources representing our experimental environment. And so we'll begin from here. After running the first cell there, the next step, we would like to create the slice itself. And we'll create a slice named SciStream and Fabric demo. That's the name we're giving to it. And the slice is going to involve 2 sites, salt and mass. with 4 nodes. Node 1 will be the producer, node 2 producer proxy, consumer proxy for node 3, and node 4 is the consumer. And then we'll specify the 3 different networks as well. Network 1, which will be the producer line, network 2, which is a WAN connection between the producer and the consumer, and network 3 or net 3 representing the consumer line. And also just naming the interfaces for each of those nodes. If you notice, we'll have only one interface here. We're specifying for node 1 and node 4, which are only connected to their respective lines in producer line as well as consumer line. While node 2 and node 3 have 2 interfaces, one in the LAN and the other connected to the WAN. Then below here, we would like to specify the kind of resources that we want to allocate to each of those nodes. So the amount of disk, CPU, RAM, what site that node would be. And then the image, the media requirement, like we talked about, we decide to use Docker and Ubuntu. And so that's what we do for all the nodes. And after setting up the nodes, we configure the network interfaces to establish L2 networks between them. This step is crucial as it defines the communication paths between our nodes, allowing for data transfer and control signals to flow through the network. And completing this, we can go ahead to create the slice. So first run the initial cell, and then next we run this cell. This is going to take some time, so I will resume the video when the slice has been created successfully, and we'll confirm that, and then we can move on from there. Now we can confirm that our slice is active with stable OK status. Let's get the IP addresses connected for each interface and each node by running this next cell. So from there, we can print out the topology, which we can see here. The producer is connected to the producer LAN network with this IP address. And the producer proxy has these 2 addresses, one connected in the line and the other connected to the WAN network. Similarly for the other consumer end as well. Next, we want to perform ping tests to establish that the producer and consumer do not have reachability over the WAN connection so far, which is typical of our use case. Node 1 cannot ping node 3 and node 4. And node 4 cannot ping node 1 and node 2. But node 2 and node 3 can talk because they are directly connected, as we see here, right? So let's just go ahead and run this trio cells just to confirm. External, build SciStream from source and install SciStream as well. First, we will, of course, install external with this command. I have gone ahead and done and run all these cells just to make sure that we don't spend a lot of time waiting on the video. So we installed external cloned SciStream from this branch and installed build so that we can actually build SciStream from that repo that we cloned, and then went ahead to install SciStream on all the nodes here. Next, let's get into the configuration, and we start from the producer side. All right, so the first thing is we're going to execute this command to be able to generate the OpenSSL private key. And from there, we're going to go ahead and use this command to echo and create a server configuration file, which will be used by OpenSSL in order to create a certificate sign-in request, which will be required to then create the certificate itself. After that, we'll move the certificate. We'll copy from the producer proxy on which we have created the private key as well as the configuration file, and then finally the certificate. We'll copy the certificate from node 2, which is the producer proxy, onto the producer, which is node 1. And then we just want to see that that is actually done, and just by showing it.
The purpose of this is just for control channel authentication, and as I mentioned earlier, we use TLS, and then in this setup, HMA is running S2UC on producer and consumer, so they need to talk to their local S2CS instances
in our directory. And finally, we delete that because we want to repeat this step again when we do the consumer side as well. So let's just go ahead and I'll run all the cells that I have explained. And then the next thing after that is that, first of all, just to confirm that, on node 1, which is a producer, we now have that certificate actually copied onto node 1. And we can go ahead now to generate the command that we intend to use to set up the tunnel from the producer side. And basically, what this command is trying to do is to initiate the control server on this port to listen with his IP address. Remember, this IP address is the IP address of the producer proxy on the producer LAN, which is directly connected to the producer itself. And the type of proxy we're using is the external subprocess proxy. That's just all that's defined with this. And then on the producer side, we'll also generate a command that we're going to use on the terminal as well, and which basically is a user client command, which is used to initiate the setup of the on-demand proxy, the SciStream, through the control server is going to set up for us. And so this is the format of the command. The inbound request is an inbound request. It means that if there's an inbound request coming to the producer proxy, same IP address and port number, and it's going to receive that traffic and forward it to the remote IP, which is a producer. And the ports on which it's going to be listening are all the ports that we have mentioned here. So you can use any of this port for actually that form of data streaming or data transfer, as the case may be. And so what we want to do next is that we would go back up and copy the SSH command for each node and then SSH into all the nodes, since we've gotten to the point where, and here is the last one. And then let's go back to where we were. Okay. So now I can go ahead and run this command on the producer proxy, which is node 2. And then run this command on the producer, which is node 1. And everything seems to go all right. Also checking the producer proxy, I can see that it has been established and the request UID is specified here, which you would see when we go to the consumer side, that it has to be the same in order to establish the tunnel between the producer and the consumer. If all went well, we should see that tunnel created that would look similar to what we have here. So that's correct so far. And this completes the configuration of the producer side. Let's head over to the consumer side of configuration things. And basically, it's a repetition of what we have done with the producer side. So I'm just going to go ahead and run all these cells for those steps. On the consumer proxy, the command is similar to the producer proxy. And so I'm going to copy that user client command. The difference is that this is an outbound request going to the control server on the consumer proxy, and the remote IP is the control server on the producer proxy. And these are the ports that are used, similar to the ports that we listed for the producer side as well. And remember, the same UID has to be quoted here and then repeating the producer proxy and the port on which the proxy should be set up. And so we copy this command and take it to the consumer, which is node 4. And it says hello sent successfully. And when we go there, it seems everything is all right. And the consumer side seems to have been set up correctly as well, which we will confirm by running this command, similar to what we did on the producer side. Next, we just want to test our proxy by running an iperf test. And even though iperf3 is already installed on this image, just in case you might want to install iperf. And then if iperf is now installed, we can just go ahead and run this test just to run the server on the producer, which is node 1, and make sure that you terminate the iPerf server after one session when it's completed. And we're running the iPerf client on the consumer in Seoul because we want the data to be sent from the producer to the consumer. We use this option for reverse in the iPerf command. And remember, we're using this port number, which is the port with which the proxy is set up, so that we can utilize a proxy for this iPerf data transfer. And now it should succeed, even though we don't have direct communication between the producer and the consumer, because there's a proxy existing on this using this port. This iPerf session or test should be successful, and data should be transferred from the producer node 1 to the consumer node 4. This would probably take some time, and we just have to wait a little bit, and I'll resume the video when I get the output from the iPerf command, which is going to come from the consumer node 4. Brief moment here, we can confirm the data transfer from the producer to the consumer using the proxy setup with SciStream. And that's basically it.
So yeah, thanks. Now I think we can move to Q&A.
Thank you so much for that presentation. We'll go ahead and begin. Oh,
I can stop the share, right?
yes, you can. Thank you. We're going to go ahead and begin with some questions now as part of the Q&A session. If you have additional questions or haven't had a chance to type them in, please feel free to do that now in the Q&A box located at the bottom of your screen. So the first question is, how do I get started experimenting with SciStream?
Oh yeah, so good question. So there is two things. We are developing SciStream as a tool to help cyber infrastructure. But you can do experiments with SciStream if you read our paper and then take a look at the repositories that we're gonna share again later. You can play with the software that we have, and that's open source software. You can see what we were talking about in our initial paper about architecture. What do we have as implementation? And you can challenge us and say like, okay, I think this can work better for the data plane, and you for instance, instead of eBPF, want to try another type of a proxy, or you want to try SDN. So look at our repo and documentation. Try to run SciStream on a local environment first. Then when you have more confidence, move into Fabric. And as you discover what are the good things and bad things, you can provide us feedback with your experimentation.
Excellent, thank you. The second question is, do I need a Globus account? Do I create the account myself, or does my university need to create the account?
Okay, yeah, so Globus is something completely different. It's similar to how you log into your Fabric testbed. I cannot remember if Fabric uses Incommons or another identity provider, but it's gonna be similar. You can go to Globus and log in with your university account. You will have a Globus account. If you want to experiment with the authentication part of SciStream, we have tutorials of how to deploy the Globus part. You can also decide that there is a different way. You can do it with other means. federated authentication. And there is also the unauthenticated part. I think we can enable you to run SciStream without using. I think that's what Acheme was doing in the video. He only used local certificates for the control channel authentication, but at no point during the demo he was reaching out to Globus. And the point of not showing this in this webinar is because we feel that Fabric is better for data plane experiments rather than control plane and authentication experiments.
Thank you. The third question is, it was mentioned that SciStream is not a streaming software. Do you recommend any streaming softwares?
I don't advocate for any streaming software. We are trying to experiment with what is available, and I think that's kind of a learning process for us as well. We have been using PubSub with ZeroMQ because one of our team members has deployed that for the specific advanced photon source use case. There is also a tool called PVA Pi that allows you to also stream images. Acheme, in fact, for his master's thesis, he experimented with just streaming ultrasound images for medical purposes using perhaps just a video streaming. So yeah, like it's up to your imagination. Even can be a completely orthogonal area of research to develop the streaming application that will use SciStream.
Okay, perfect. The next question is, can you talk about some of the SmartNIC features you used with SciStream?
Okay, yes. So we were just using the plain SmartNIC because we wanted access to the 100 gig line rate. We could, in the future, look at other features. I'm aware that Fabric allows you to use FPGAs and then use P4. Maybe someone can develop an S2DS implementation that is, instead of eBPF, is completely based on P4 and uses the smart NIC options that Fabrics allows you to or give you access to.
Great, thank you. Okay, so the fifth question we got for you. Are the science streaming pre-recorded data sets available for people to experiment with?
That's a good question. So we don't have and we don't maintain any data sets for the streaming applications. I believe that some of the applications we have can generate dummy data. So in fact, for that HPDC paper that I showed at the beginning of the talk, we were just generating the size of the samples as just writing a blob into memory and then put that into a file, an object that was then written into ZeroMQ. So because we were more interested in performances rather than real data that was being streamed. But it's definitely an interesting area to look at because it's not always you're gonna get like uniform data of the same size. Sometimes your experiment is gonna adjust rates or sizes for any kind of optimization. So yeah, that's kind of future work.
Perfect, thank you. Okay, how fast have you seen SciStream work so far on Fabric?
On Fabric, we have those 2022 results that I think we were able to achieve 87 megabits per second. Of course, we were using 5 different topologies, 5 different topologies. There were other experimenters, So if you are familiar with the supercomputing conference, SC, in this was a workshop inside SC. So you imagine how many people were running experiments at the same time on Fabric for that conference. So we were kind of competing for bandwidth with them, but still we were able to achieve a lot of bandwidth. We recently tested 5G, sorry, a SciStream on the ESNet test, but ESNet is the energy science network, and ESNet is the substrate for Fabric. We were able to achieve really close to the 100 gig line rate, even with these commercial proxies that we have now. And that was demonstrated at SC23 as a demo.
Great, thank you.
Yeah, gigabits per second. Yeah, thanks, Casey.
So just for a clarification, there was a question that came through that asked if it was 87 megabytes or gigabytes, and so
yes, it's
yeah.
gigabits per second. Yeah, sorry,
so
I misspoke.
yeah. Okay, well, that was actually our last question. So I want to just give another thank you to our speaker, Joaquin Chung. We really appreciate you being here. In addition to our presenter, we would also like to acknowledge some behind the scenes people who really make sure and work diligently to bring this webinar to production. And so there's a slide of the people that I just wanted to acknowledge there. If you could please go to the next slide. I also want to thank the audience, you all, for attending and your participation in today's webinar. In addition to a recording of this webinar, we will also email everyone who has registered a list of resources. This slide deck will be shared along with a link to our Slack channel and Connect with Us form. So we hope that you will reach out to the Fabric team for questions or support. We have a webinar tomorrow, Mastering Fabric Tips and Tricks webinar, Network Interfaces, led by Paul Ruth, and it is at 3 p.m. Eastern. This webinar is geared towards existing Fabric users. And then next month, we have 2 additional webinars. The first is Mastering Fabric Tips and Tricks webinar series, and that will be on Monday, September 16th at 3 p.m. Eastern. And the second is Stitching Together Innovation with Fabric Users, which will be on Tuesday, September 17th at 2 p.m. Eastern. The September 16th webinar is geared towards existing users, and the following webinar on September 17th is geared towards new users. So we would appreciate it if you could forward the information to any relevant user in your community. As a final reminder, please submit your Fabric matrix and make sure your project abstract in the portal is up to date, as we will use that information for outreach, including our website. So thanks again, everyone, for joining, and we hope you have a wonderful day.
Thanks for having me.